So before I start, any questions? Does anybody have any questions about the stuff that was done in last class with TFS and its applications in topological sort? Yeah.
Hello, sir.
Yeah.
Topological sort is unique, give uniqueness or not?
No, topological sort doesn't give a unique name, of course.
Sir, if there is a Hamiltonian part, then it is
If there is a Hamiltonian one, then that will be an unique one.
but how can we prove this?
Okay, cool. Try to prove it. Okay. So if there is a Hamiltonian path, so what you have to use is the fact that it is an acyclic graph as well as it has a Hamiltonian path.
Yes, sir, if it is cyclic, then we cannot use the.
If it is
Topological
cyclic,
sort.
if there is any cycle, then there is no topological sort.
Yes, sir. If there is any cycle, then we cannot use the topological sort.
Yes, not algorithm. There is no topological sort. I mean, how can you sort something? How can you sort something? Yeah, sorry. Yeah, so if there is a cycle, then of course there is no sorting because you can. I mean, a cycle will say that you have to do A before B, B before C, and C before A, right? And that is not going to work, right? So a cycle, any graph that has any cycle, that graph doesn't have a topological sort. So a graph has to be acyclic. And you are saying that what happens if the graph has a Hamiltonian path? Okay. Now, if a graph has a Hamiltonian path and it is cyclic, then my claim is that that graph is a straight line graph. That is, it's a path. That's it. There's nothing else. Okay. Because even if there's a Hamiltonian path and you have any other edge in that graph, then you produce a cycle. Right? Actually, no, that's not true. Actually, that's not true. Any backward path is no backward. There can be forward paths. Hello.
Hello, sir.
Yeah, yeah. Any other questions? Is it clear? This one, whatever I told just now.
Sir, if it is cycle, then we can get an back path, backward path.
If there is a cycle, then you will get a backward path in your by your DFS. Right?
Yes, sir.
Yeah. See, I mean, what I want to say is that there are two things. Number one thing is that number one thing is that there is this concept of a topological sort. Okay, a topological sort just says that it's a sorting of the stuff of the event so that all the rules are maintained. Okay, and the other thing is that DFS. Now DFS gives you a topological sort. So don't you may think that DFS. I mean, if DFS cannot find a topological sort, so whatever DFS finds out is unique, that means the topological sort is unique. No, that is not the case. Okay, but what I want to say is that any graph that has a Hamiltonian path, there the topological sort itself is unique. There's only one way of sorting the event. Of course, DFS will find that event, that sorting, but there's only one way of sorting that. So is it fine? Does it clear answer your question?
Yes, sir. But if there is a Hamiltonian path, but this is the topological sort is given uniqueness, but
Yeah.
I stop.
If there is a topological path, so you are asking how to prove that if there is a topological path, then how is it that there is only unique path? Unique
I did not want to prove, but intuition, if any intuition. this thing.
Okay, so if you have a path, okay, so let me share my screen and you can you see my screen? Hello.
Yes, sir. Yes, sir.
So say I have a graph, okay. So I have a graph, okay, and then there are lots of paths, but then there is a Hamiltonian path, okay. Whatever, doesn't matter Hamiltonian path or some path. Okay, maybe there are some other edges also. Okay, maybe there are some edges like this. Okay, this cannot be the edge. There is an edge like this. Edge like this. Correct. There can be a lot of edges. But see, once you have this path, what does it mean? Right? As we kind of told last time, that you always start from the vortex, or you have to start from a vortex which has 0 in degree. Right? Fine.
Yes, sir.
So 0 in degree basically is this one. So this has to be the first element. Right. Now, if you take this first element out, okay, so this is the first element. Okay, so you imagine that this is the schedule that you have to do. So this is the first element that you have to do. Okay, you take this one out. Okay, so now my graph is basically this graph. In this graph, also you have lots of edges. So this is the first element. After that, I will do the next element. Which is the next one that I do? See, there is only unique every time. So there is a unique vertex, which is again the 0 in degree. So that means I again have to, here also I have to put this one to be the second element. This is the first, this is the second. And similarly, you can keep on doing it, right? Similarly, if okay, what I forget this one, and I consider this graph. In this graph, any graph or any subgraph is saying that, okay, among this set of vertices, which, I mean, is there an ordering? See, if a graph is acyclic, then the subgraph is also acyclic, right? So here also, among this set of vertices inside the green border boundary, which one has to be done first? It is the one which has 0 in degree. So if there is multiple vertices of 0 in degree, right, then I could have chosen any one of them. But because of this Hamiltonian path existence, right, I have just removed the first 2 vertices in the Hamiltonian path. So the remaining Hamiltonian path seems to exist here, right? So there is only one vertex that has 0 in degree, right? So again, this has to be therefore among this set of vertices, this has to be done first. So there will be first, second, and this will be third, and so on. So this will show that if there is a path, you have to follow that path, nothing doing.
Okay, I understand it.
Okay, if there is a path, then you have to follow that path. Okay.
Okay, sir.
Any other questions? Okay, if there's no other questions, let me just then go straight into the. So we have been doing things of this depth first search, right? As we told you, depth first search is basically studying in a way in which you kind of want to take a subject and study that subject in as much detail as you can, and then backtrack and then study the next one and so on and so on. But then there is the other thing called a breadth first search. Breadth first search. So breadth first search is something you will understand a lot. This is something that is done a lot in the maybe certain management courses and various of the many various schools or various courses done, in which you are not given a detailed study on any subject, but you have been kind of told a little bit of everything. And now, once you have got the understanding of a little bit of everything, then you go into the next level. Okay, now let me go into a little bit deeper and then do a little bit of everything else. So basically something like, if I have a graph like this, Okay, I mean, I'm just drawing a random graph. Okay, so say if I say and I start with this vertex. Okay, so this is the vertex I am first there. Okay, this is my node vertex. This is my root vertex. Now, once I'm done with this one, which is the next vertex that I should look at? So idea is that I would look at all its neighbors in one go, one after another. So in this case, the neighbors are this and this. So you can think of that. So this is the starting point. This is the starting vertex, and you are looking at all the things that are just one level below or one distance away from the root vertex, and you do all of them. Okay, so without loss of generality, I can say that this is the second vertex and this is the third vertex. So now at this point, I've started from the root vertex and I've gone and seen both its neighbors. Right? Now, what do? I want to go one step deeper. So you can think of these are like the high level things about the various subjects. The two subjects I am teaching both the subjects at slightly high level. Now I said, okay, let's look at the first subject. And let's go a little bit more deeper. Let's go into the first chapter. So what do? I go to the first chapter. I go to the 2 and go to the first chapter. Now, if in that case I will go to all the chapters, but it has only one chapter in this case. So I'm done with it. I don't go further. I don't go into a sub chapter kind of stuff. Instead, I move to this 3 and I look at all the other chapters from there. So maybe this is already has been addressed. So I go into okay. So in some sense, this becomes the 4th vertex and this becomes the 5th vertex. So at this point, look at this one. This is all the vertices at distance 1. These are all the vertices at distance 1, right? These are all the vertices at distance 0. These are all the vertices at distance 1. And these are all the vertices at distance 2. I'm done with that. Meaning you can think of it that I have completely finished studying everything at level 2. Now I want to go for one more level. I have some more time. So I go to this 4th vertex. So among the distance 3, all the vertices that have among the vertices, which vertex I have looked in first. And now I go into all its sub vertices. Oh, sorry. Yeah. I go to all its sub vertices. I go first here, then here, then here. So this will be the 6th vertex, 7th vertex, and 8th vertex. See, in one go, whenever I'm at a vertex, when I'm considering a vertex, I will look at all its neighbors. Instead, in the case of DFS, what we are doing, we are looking at one of its neighbor, then going into that neighbor and going further ahead like that, right? So here that is not the case. When I'm at a vertex, I'm looking at all its neighbors. I'm doing a breadth. I'm covering a larger breadth of the subject. Once I'm done, I go to the 5th vertex and I do this 2, right? 9 and 10. Now, okay, I am done with this thing. So at this point, all these vertices are at distance. So this one was distance 1, this is distance 2, and all these vertices are at distance 3. And now I'll go into all these vertices one by one and see if there is anything left to be looked into in this graph. It is not there, and we are done with it. So the graph that it will come up with, if you think of it, okay. So I first had looked at this one, and then I looked at this one. Then I considered 2, and then I looked at this one. Then I considered 3, and 3 and 4 was already discovered, so I looked at this one. Then I looked at this, and this, and this, and this. So this becomes now the BFS tree. Okay. So if instead, say, if I had done this, if I had, what would have happened if I had done the DFS for that matter, for this exact tree? Can somebody say? Maybe I can use a different color. Maybe I use color. Okay. So in that case, if I had done DFS, I would have depth first. I would have gone to 2 first. Then from there I would possibly gone to 4. Then possibly I would gone to 5. Then I come back to 7, to 8. Then I have gone to 3. Okay. At 3 I would have gone to 5. And 5 I would have gone to 10. And then I would have gone to 9. And then I would have come back and kept on finding out that nothing else is there. So you see that these two completely different style of graph that exist here, right? So, so this is what is called a breadth first search. So the green one is of course the depth first search. So let me go over the breadth first search also in a bit more details once again.
Sir, from 4.
Yeah, sorry.
Sir, from 4, shouldn't we go to 5 in depth first?
I mean, it doesn't matter. It matters about which one of these two things are.
Because 1 to 4, when we're traversing 1 to 4,
Yeah.
so from 4 we can go 5 also.
We can go 5 also. We can go 5 also. It depends upon in the
Depth first search we should go.
no, it's not what whether we should go or not. It is
From 2 also, we can go to 3.
we can go to 3. It all depends upon how is the the neighbors in the adjacency list of 2 or adjacency list of 4 is ordered.
For example, if we start from 1, so adjacent is first if we choose 2, from 2 we have okay, from 4, 2 to 4.
It depends upon how you are ordering it inside the adjacency list.
Okay, sir.
So again, you should realize this one: depth first search and breadth first search. Neither of these two trees that you get are unique. It depends a lot on the ordering. Okay, it depends a lot on the ordering of these vertices. For example, let me tell you one simple one. Okay, maybe I will go back here a bit and let's forget this one. Okay, let me not go into this. So I am talking about the red ones, right? See, at this point, so I am at 1, I have done 2 and 3 in breadth first search. I'm now in breadth first search, okay? Okay. Now, if 2 or 3 was before 2 in the adjacency list of 1, then I would have considered 3 first. And when I considered 3 first, then I would have gone to first 4 and then 5. Both of them together, is it 4 and 5? And then 2 would have nothing else in it to go to. Okay, and then I would have gone to 4 and I would have to go and look at both of them. And from 5, I would have. So this is how it would happen if 3 was before 2 in the adjacency list of 1, which is considered first. Okay, is it clear?
Yes, sir.
Yeah. So
Sir, one question, sir. Like, can it ever happen that BFS and DFS both are yielding the same result? Like
yeah,
we
of
see
course.
here.
Of course. So think of the graph to be a straight line,
Oh, okay, yeah.
or a graph is a tree,
Huh.
right? If the graph is a tree, it
Yes,
will
then
output a tree.
yes, sir. And sir, one more thing here: the number of edges, like, and in the BFS tree and the DFS tree, finally that you show that the graph were different, but the number of pages, I found out that they were same. So will it be generally like, will that happen generally every time?
So Louis, you have done a discrete math course before?
Yes, yes.
How many edges are there in a tree?
Oh, okay. Oh, sorry. So sorry. I understand that. Sorry, sir.
It has to be same always.
N-1, yes, sir. I'm so sorry. I'm so sorry.
Okay. Any other question? Okay. So this is actually good that you are asking this question, because it is important to note that DFS and BFS will not yield a unique space. That is actually a very important thing, and it depends all about the ordering of the vertices in the adjacency list. Okay. Okay, so let me go over this BFS once more in a set of graphs. Yeah, so this is basically the BFS thing is basically start from a vertex, find all its neighbors, then find all the neighbors of the first neighbor, and find all the neighbors of the second neighbor, and so on. So just like in the case of, maybe I can go back here a bit. In the case of with DFS, one of the data structures that we had used is stacks, right? Is stack. What is stacks? Stacks was basically, it is the last in, first out. Right, whatever goes in first, they keep on piling up, and then whatever went in the last, once you pop it out, the top one goes off. And this is the thing that we use. In the case of BFS, we will use another data structure, and that is called queue. Now, what is a queue? A queue is basically you have something and you push it in. Okay. Okay, so there are two operations you can do. You can do NQ and DQ. Okay, so NQ basically means that you just push it in the queue. I mean, we all know what are the queue is, right? I mean, you stand in a line and you go in, right? A, B, C, D, one goes. But what is a DQ? So NQ of A meaning you push in A inside. NQ of B meaning push in B inside, and so on. Right? And DQ doesn't take anything. DQ basically just takes out the one which is first in the queue. So whichever comes in first, they should go out first. Okay, so this is called FIFO. First in, first out. Okay. Now both these things I have not actually explained how to work on this stacks and queue. Okay. So what I will do is that, I mean, I would ask you guys to think about how to implement stack and queue. Okay. It is a data structure. If you have done a data structure course, hopefully you have seen stacks and queues. And if not, using simple things like a double linked list and all, you can get all of them done. So basically, in the case of stacks, we have the push and pop, just like push something and pop, push and pop, and here you have NQ and A. In both the cases, you can do it as quickly in terms of in order one step you can do. I'm curious. So the MTech CS students, you have done some data structure course, right?
Yes, sir.
I mean, was stack and queue done in your course?
Yeah.
Okay. And what about the JRS? You have all seen the stack and queue? Hello.
Sir,
Yeah. So you guys are familiar with stack and queue. You guys also did this data structure course.
yes,
Yes, sir.
sir. Yes, sir.
And what about the MTech CRS? Did you
Yes,
have a
sir.
data structure course?
Yes, sir.
You also had adjusted.
Yes.
Excellent. And you all also you have done stack and queue, right?
Yes.
By the way, just okay. I mean, is DFS and BFS already done in data structure course?
Yeah,
Yes,
it
sir.
is.
Some part.
Some part of it. In both the courses, MTech CS and MTech CRS, both of them.
Yeah.
MTech CRS also. Who is there from MTech
Sir,
CRS?
stack and queue is done, but
No.
DFS and BFS, was
Actually,
discussed
sir,
while talking about stack and queue.
Okay, okay, fine. Okay, anyway, DFS and BFS are two very basic things, so I don't mind doing it again. So let's put that we are doing it. Okay, so here is an example of this BFS, right? So here is the graph, and I am going directly on the directed graph. Okay, so just like in the case of DFS, we talked about directed graph. Also, we can do that. We can do the same thing. And in the top of it is the Q. Okay, and we start with the H. Okay, so here I'm talking about BFS starting from H. What do? You push it in the queue. As soon as you start, you push it in the queue. And every time you look at the DQ, look at the top of the queue, okay, and whichever the first of the queue, and whichever vertex is in the front of the queue, you will consider that. So at this point, I have H, and I look at all its neighbors. Okay, so our job is this following. I will look at the edge vertex at the top of the queue, at the front of the queue, and I will take that vertex out and look at all its neighbors and push all the neighbors into the queue. So here I take H and I take G, I look at its neighbor G and push it into the, not push it, put it in the queue. And now H doesn't have any more neighbor, so H should
G
be
should be
yeah. Sorry.
H should be at the front, right?
Yeah, so H is in the front, right? So I have not kind
Okay,
of
so
thrown
in
away
this.
the H. Okay, in some sense, what I'm doing is to look at this pointer. You can see the pointer. So the pointer will
Yes,
indicate
okay.
the front of the queue. Okay, so NQ will basically DQ will output the vertex at that pointer level. So the pointer will always go from the left to right. I mean, you can think of that at this point, H has been DQ completely. But just for our own understanding, we are keeping it in this queue. And the pointer is basically what is going to point out what the front of the queue is. So look at this one. At this point, the front one is G. Okay, pointer is pointing at G. So I will look at G, look at all its neighbors. In this case, it's E and F. I will take both of them. I will put it in the queue. E and then F. Okay, and I basically DQ the queue. So that means I move the pointer from one step ahead. At this point, I go to E. And now E, I will look at all its neighbors again, and I'll put all the neighbors one by one in the queue. C, B, and T. And I go to F, which is the next one in the queue. And F doesn't have anything else to be done. Okay, since it doesn't have no other neighbor that is already not been put in the queue or has been marked, right? So we move on, and basically all we do nothing. We just look at all of them, and I move the pointer one step ahead. That means we kind of DQ the, and we are now at C. Again, C will also have nothing to be done. Look at B and we find out, okay, nothing to be done. And move one step ahead. At this point, I look at B, and B will have the thing at A, as a neighbor A. So I consider A, I'll put A into this thing. I go to this next one, which is D, and at D also I find that, okay, there's only A is there. So I just observe it and I come to the end of it, and basically that's it. At this time, I will DQ the Q and the A will also go off and my Q will be empty. Okay, so is it clear what's going on here? That at any point of time, I'm looking at a vertex and saying that, okay, who are all your neighbors? All the neighbors one by one go into the Q. And that's it. And I continue like that. Okay. So this is basically the two things that we use, NQ and DQ. And here is the simple pseudocode for this one. So we start with an empty Q. Everything in all the vertices initially are colored gray. At any point of time, I'll start with NQing this V. V is the one that has been given to us. This is the vertex from which we start our BFS. And while the Q is not empty, I do is that I will DQ the Q. So which is basically look at the topmost or frontmost element in the Q. Now for all the elements in the neighbor, okay, if they are gray, meaning if they are not visited, then I will select this edge and NQ that. And else, and at the end of the day, I will color, and once I have visited that vertex, I will color that vertex. And I will remove that vertex from that. Actually, this part is not required, actually speaking, because we are going to look at the neighbor of U only once. If you go along on the adjacency list of U one in a linear fashion, then also this will give you the correct answer. So this is how the pseudocode for the BFS will look like. It is very similar to, I mean, not very similar, it is kind of very simple. And BFS uses stacks and this one uses. Okay, so any questions? Okay, so let me actually ask you one thing. So here we have got something idea, right? I have a graph and I have got a thing. Now think of this one, okay? So this is my graph. My black vertices are my graphs. They're all directed vertices. Okay, now tell me one thing. Okay, so there's this one, and now there are this not so. I mean, these are the red ones are not non-edge, non-free vertices, non-free edges. Okay.
So red one is?
They are the non-free edges. These are the edges that are not in the DFS tree, but they are in the graph.
Okay. Okay.
Okay. Yeah. Now, yeah. So there are some of the. Can you tell me which of these edges are not? I mean, can this be a BFS tree? Can this be a proper representation of a BFS tree? For example, let's look at this one. Is this edge possible?
Yes, sir. It should be in the BFS tree.
It should be in the BFS tree.
Yes, sir.
Why?
Because immediate edge of 2, right?
Immediate edge are
Immediate edge of 2 vertex 2.
yeah. So which should be in the BFS tree?
So like edge 29 should be in the BFS tree.
Exactly. So edge 29 should be in the BFS tree. right? So this edge must be in the BFS tree. So this edge cannot be this cannot be a non-tree edge. Okay. So that means, so these are called the forward edges. Okay. Let me write down here. Forward edges. Forward edges are forward edges. So these forward edges are not possible in a BFS tree. Okay, that means if I give you a tree, then this edge cannot be saying, oh, there is an edge like this. It's not possible. Forward edges are not possible. Is it clear for everybody?
Yes, sir.
Even the middle one also, 2 to 3, that
2
edge,
to 3. What do you think? 2 to 3, there or not?
not there.
Not there?
2 to 3, this is in red, but it should be traverse, right?
No.
In the
Why?
BFS.
Can you say why?
We explore
See,
the
when I'm
adjacent
looking at
vertices first.
When
when I'm looking
adjacent-
at one,
yes,
right? I'm looking at both the, so this is first of all in the queue. Then I will look at all these neighbors, which is 2 and 3,
neighbors. Oh,
right?
yes, yes.
So cross edges is a possibility. And these are basically what is called a cross edges within layer. Cross edges to, so this is a cross edge to what? To siblings. So these are the brother or sister of 2, right?
Hmm.
So these are called cross edges to siblings. These are possible. Okay, it is very much possible. Cross edges to siblings. That is not a problem.
Yes, yes, yes.
Okay. What about this one? 4 to 11. What about this one? 4 to 11.
4 to 11 must be there.
Must be there. Must be
Yes.
there meaning what? What does we mean by must be there?
Must be there means if from 2, if the adjacency list is 4, 5, 6, 4 is the front. If 4 is in the front, then 11 should be there.
Correct.
4 to 11 should be there.
Yeah. So this is basically a cross edge to, okay, to child of a sibling. Okay. So if this edge, so consider the case. So these 3 are of the, sorry. Yeah. So this, all of them, 4, 5, 6 are in the same level, right? 4, 5, 6, 7, 8 are in the same level. So that means all of them, there was a time when all of them must have been in the queue, right?
Hmm.
At that time, say 4 was being looked into. If 4 is looked into, then 11 will be done, right? Has to be taken. But at the same time, if 6 was considered first, then I would have considered 11. And at that time, that is not a problem. Okay. So this edge can be there and maybe there may not be there depending on the ordering of 4 and 6 in the adjacency list of 2. Okay. So if 6 is considered before 4, then that is not possible. Okay. So, sorry, so then it is possible that there is an edge from 4 to 11. But if 4 is considered before 6, then 11 must have been considered before. So in some sense, you can think of the cross edges, okay, can or cannot or may not happens may or may not be in the BFS tree depending on the ordering. So one thing that is not possible, certainly we have got hold of, is forward edges. Forward edges is just not possible. Okay. Now even the back edges are possible, very much possible. There might be possible back edges, and even this, all this kind of cross edges are possible. But again, there's one more thing. This cross edges has to be across a distance of 3. So maybe I should maybe make one more picture. Okay, what happens? Say I have another edge like this, and there is a edge from 4 to 13. Is 4 to 13 possible? What about this edge, 4 to 13 edge?
Yes,
Is it possible?
possible, sir.
What will mean possible?
Possible means it's possible. From 4, if 4 comes first,
Yeah. If
the
4
ordering.
comes first, then of course 13 will be taken, right? 4 to 13
Yes.
edge will be taken. But is it possible that this is not taken?
5 to 6, then 6, 11.
This is not possible, sir.
Yes, this is not possible.
Why not possible?
This
See,
is
this is-
because any of the 4, 5, 6, if it is in the, like, any of the ordering will have 13 in force adjacency list. So no-
Exactly. But let's go into a bit more details, okay? So what are these edges? What are these vertices? Can somebody say what are these vertices? So these vertices are all the vertices at distance 0 from 1. These are all the vertices at distance 2 from 1. Sorry, 1 from 1.
one.
These are all the vertices at distance 3 from 1. Right? These are all the vertices that are distance 4 from 1. Now this vertex is at distance how much from 1? This vertex is at distance how much from 1?
3, sir.
This vertex is at distance 3 from 1. 1, 2, 3. Right? So this vertex cannot be in this layer. This must be in the above layer, if at all. Okay. So this is something very important. So a cross edge is not, or any edge, a cross edge is not possible across more than across layers of at distance more than or equal to 2 apart. Okay, so if I have this layer and this layer is at distance 2, right? So that is not possible. So this is another thing that is beautiful part of this BFS is that I will always, if a vertex is there at distance k from 1, okay, from a particular root vertex. So I have a root vertex, here is a root vertex, and I have this graph, and there is a graph vertex that is a distance. Now what is the distance meaning? The minimum distance of this vertex. So this is a root u is v, right? If the distance is k, then this in the tree, where will this vertex v remain? In this tree, starting from u, the vertex v will have to be in the depth k. Okay.
Yes.
So this is a beautiful part of BFS. So you do BFS. So it's in some sense you can say you are at your home and you want to find out the distance of say a particular vertex from your particular place from your home, what do you do? How will you do it? One way is to do BFS. Okay, and look at BFS, look at the defined time when the vertex arrives, and look at the path on the BFS tree. It's a unique path. In a tree, you have unique path, right? And that will give you the distance. So a BFS can also be used to find a shortest path between two vertices or any vertices from the root node. Is this clear?
Sir, that age in the top portion, that age to 13, we
Two-
cannot tell. Yeah, that last age we discussed from
Yes,
4 to
yes,
13.
yes.
Yeah, that age we cannot say as a forward age, is it?
No, this is not a forward. Forward edge is something to your descendant. So 13 is not a descendant of 4, right? In the graph.
Yes, but descendant of sibling.
Yeah, I'm saying that the descendant of a sibling, but it's not considered a forward.
Okay.
Yeah, forward edges are usually like this. Okay, anything that goes forward. This is a cross edge. There can be multiple kind of cross edges, but a cross edges is not possible at distance greater than 2.
Yes, sir.
And DFS, this is a beautiful part of DFS. DFS finds out the shortest distance.
Sir, shortest distance will depend upon the weight of the edge, right?
No, I mean, assuming that all the edges are weight 1.
Okay.
Okay, I mean, I use all the edges are weight 1, and in that case, the unweighted term. Okay. All the edges, I mean, the shortest distance is the length of the shortest number of edges from that vertex to. Okay, this is currently what I am discussing about shortest. Okay. Yeah. So of course, the BFS can be used for checking connectivity. That is obvious. Okay. And there are these free and non-free edges and all those things that we just now discussed. The running time, okay, you can very quickly see that the running time will be linear, because anyway we are going over every edge exactly once. That's it. Once we are going over one edge once, we are removing it from the adjacency list or from the thing. So we are doing it exactly once. So therefore, we are doing the running time of this one is just a linear. And one of the best important thing of BFS is that it helps us to find the shortest path from the vertex. Right? So yeah. So run a BFS from that vertex and you will get to find out the shortest distance. So here is another thing. Okay, so I mean I've just done that same thing. So this is the top one. I've just given an example where the top one will basically just point out all the distance from H. So if you just see that the distance from H, so this is 2. These are basically all the, if you just layer the edges of the tree, then this will be at the level 2, right? And similarly, all of them will be at level 3 and level 4. So you can easily, by doing a DFS, you can keep track of. I mean, basic idea is that if you just go back a little bit. So when you are looking at say E is of distance 2. But anything that I am going to put in by while looking at E, so which is B, C, D, and B, they will have one more distance. So 3, 3, and 3. So by doing that, by maintaining basically two arrays, you can find out all the shortest distance from a vertex to all the vertices. Now again, I should remind you guys, this is also, as someone of you pointed out, it is only the shortest distance when the distance is measured by the number of edges, not the, it's not a weighted graph. It's not the sum of the weights on the edges. It's all total the number of edges. We will soon study the thing about how to find out when it is the number of when the sum of the edge weights, but we will do it only in maybe next week or something. Okay. So yeah. So you can output the shortest distance from a vertex to all the vertices in linear time. And basically that's it. So this is all about the BFS. And let me not, I mean, if you have any questions and doubts, let me, I mean, please ask me. I'll be happy to answer them, clarify them as much as possible. Okay. But in terms of, yeah, in terms of presentation, I think this is all that is there that I have for BFS. So if you, I would again encourage you guys to please go and look at the BFS and DFS from any of the books. I'll be happy if you guys can, I mean, you can come back and ask us questions about what the doubts and all those kind of stuff. But yeah, it will be pretty useful if you, for yourselves, to go over the book to see how the DFS and BFS, the proofs of topological sort, and all of these things are written. Okay. Also, the books will have some very nice exercises on BFS and DFS. Something that would be useful for you guys. Yeah, to do. We will be posting you a problem set, hopefully tonight, maybe tomorrow, and there will of course be these two tutorials on Saturday and Monday. So please try to attend and try to give some come with your doubts and all. Yeah. Any questions? Okay, so if you don't have any questions, then I will stop the class today. It was a shortish class, of course, but that's fine. So this is an important aspect of graph algorithms, BFS, DFS, and their applications. Okay.
So which one is used, like,
More?
the application of BFS and DFS?
Both
like,
of them have their
where-
own applications, right? I mean, that's which for the two important things. Like topological sort is a very important thing that is used left and right in various places, right? And finding shortest path is another thing that is shortest path, and all is another thing that is used a lot. So basically, one thing is that you should realize that both of them are traversal algorithms. That is something important. Okay. So particularly if I have something hidden somewhere, so I have a graph, and I have a graph that is hidden somewhere. How do you find out? You do a DFS or BFS algorithm. A good example is basically all the search engines. They do BFS and DFS on the graph network, I mean the network graph of the internet. Okay, so all of this kind of, so now depending on whether So they follow the hyperlinks to go keep on going from one to the other. And they will have to do some kind of BFS or DFS kind of a thing too. They have heard all the nice terms of web crawling and all those things. They are basically a clever usage of the BFS and DFS, and that's it. Depending on yeah, so then there are also like other things that you have that are there. How do you order the vertices in terms of the adjacency list and all those things? Which ordering should you consider? So all of those things do come up in the various applications depending on the problem. But these two are very, very, very important stuff to be kind of looked at. Both DFS and PFS. Both of them has their very important, quite important. A DFS will in generally create a skinny tree, a tall tree. A BFS is expected to create a wider tree, a fatter, with less depth and more spread. So that is two things that is there. Now there are applications in which one tree is used over the other tree. A skinny tree is better. Some applications, a fatter tree is better. And those things will be done. So, yeah, so most important thing is that both of them are traversal algorithms, which is something that you should kind of always keep in mind. So that from now on we can say that, oh, find whether a vertex has a degree 5. How do you do it? Do a BFS or do a DFS. You traverse the graph and keep on checking for the degree. Okay, so searching for such kind of stuff, any traversal of the tree can be done in linear time. A very important concept.
Hello, sir.
Yeah.
Sir, if we give input in two different ways, then the running time will be same or different?
Running time will always be same. The running time is based on only the edges, right? You're going through the edges. You're going through all the edges exactly. In the case of directed graph, you're going through all the edges exactly. Okay, so the running time will be same, both in the DFS and BFS. So this is also you should realize that in both DFS and BFS and in any traversal algorithm, the idea is not only to visit all the vertices, but it's also to visit all the edges. Okay. And this is something very important. Let's say I will have examples in which I will just tell, oh, consider the edge with the maximum weight. It's a weighted graph, consider the graph edge with maximum. How do you find the maximum weight edge? You do a BFS or DFS, it visits every possible edge, and so you can always keep a tab on what is the maximum edge weight that you have seen, right? So that's a traversal. So graph traversal is not just traversing all the vertices, it's traversing all the edges. And in both the graphs does that. So in terms of running time, both the graphs have same running time. It's all about the final out, the BFS tree and DFS tree. They are structurally different. Okay.
If you give the adjacency matrix as an input, then it will take more time.
Oh, if you give the adjacency matrix as an input, okay, then you don't take exactly more time. Then you can also do that. You can think about it. But this is the adjacency matrix is, yeah, it will take more time in the sense that it will take order n square steps, not order n plus n. But that is within the input itself is order n square. Right. If the input itself is order n square, you need n square steps to kind of see all the bits. Right. So if you take if the input is essentially a matrix, then the input is at order n square and the algorithm is also running order n square.
then it will be not the linear time. It will take the
Yeah, but
quadratic
in
time.
the input, it's linear in the input side. You're giving me a
Okay.
big input. So what can I do? That's not my fault.
Okay.
Right? Give me a smaller input, I will do that in the smaller. I mean, you have to give an algorithm enough time to read the input, right? If you-
Okay. This algorithm is linear to the input.
Yes. When we say from now on, whenever we will say things like linear or polynomial or something, it's always it is linear or polynomial to the input size. Okay. It's a very crucial concept that you should always keep in mind. Okay. Okay. Any other questions? Okay, so if not, let's stop the class now. I will let you guys know what I will teach on Tuesday. Maybe I'll send a mail or something like that, or a post or something. But I will not ask you guys to kind of read up anything new. All I'm saying is that go and just get yourself familiarized with DFS and DFS from the book. Do the exercises, do the problems, and that's it.
Sir,
Only-
in the
Yeah. Go ahead.
mid sem,
Yeah.
like up to this part will be there, no?
No,
Next week.
in the midterm, everything till whatever we will be doing till the end of the next week. See, I don't believe in all of these things or this kind of exam and all those kind of how much is the syllabus for the exam and all. Okay, you come to the class. If you come to the class and you do the basic stuff that has been asked by you to be done, you will find the exam easy.
Okay.
That is, by the way, you have not yet told me about when the exam will happen. I hope that you will tell me sometime soon.
Sir, I think 20. When is the date? I think 20 May. I think 22.
Okay, so
Next week, I think.
why don't you confirm and let me know? 20 May.
Okay. Okay.
20 May.
Sorry, sir.
No,
It is
the
not even
midsem is 24 to 29, sir. That's the week.
Yeah,
that's
that I
the
know.
week.
But which day you want your this mid-sem?
Yeah, we'll discuss in the class. We'll
Yes,
show you
yes.
the
You
details.
discuss in the class and later.
Sure, sir. Yeah.
Okay, good. So I will see you on Tuesday, and some problem set will be posted, and maybe sometime early next week there will be an assignment.